The technical debt local AI must fix before it's too late, what NemoClaw says about NVIDIA's philosophy. If you've been following my recent posts, you might have seen my repository and the issue I opened on the NemoClaw repo, number 315, while architecting this solution. The dialogue captures the why behind the how, and led me to a deeper realization about a fundamental design flaw in the entire local AI ecosystem. User. I've read through NemoClaw's dump on the sandboxes, with explicit whitelists only for NVIDIA's API endpoints. The threat model is clearly zero trust with the host OS treated as hostile. I bypassed it with a TCP relay on the Docker bridge to reach my local VLLM. Walk me through what NVIDIA is actually defending against here, because my relay arguably strengthens the data boundary, not weakens it. Assistant. User. My concern is specifically about API exfiltration in agentic contexts. Enterprise TOS says, we don't train on your data, fine. But an agent with shell access runs across the workspace, streams the output into its context window, and sends the full prompt to the API on every turn. The attack surface isn't training, it's the transmission itself. With prompt injection in the loop, this becomes an automated exfiltration vector. How does that change the risk calculus versus a standard chat interface? Assistant. User. Here's what I don't understand about NVIDIA's product strategy. Nematron is their own model, optimized for local consumer GPUs. NIM is their inference serving layer. DLLM is heavily NVIDIA-backed. NemoClaw is their sandbox. They built every component of a fully local agentic stack, then shipped the sandbox with a default policy that blocks it. The pieces exist, but the network policy doesn't acknowledge their own ecosystem. Is this just an enterprise-first design that hasn't caught up, or is there a deeper architectural reason? Assistant. User. I think I see the structural issue. DLLM exposes. OpenAI's cloud is. Same REST interface, same JSON schema, same HTTP semantics. At the /kernel level, both are TCP sockets carrying HTTP, structurally identical. The sandbox can't distinguish them because the protocol is the same. The community treated OpenAI-compatible as a feature, but it means local inference is indistinguishable from a cloud call at the system level. Assistant. User. So the community has a collective design debt from adopting OpenAI's wire protocol wholesale. Compatible was never a neutral technical choice, it carried an implicit architectural assumption that inference is a remote network service. We brought the model onto our own hardware but kept the cloud serialization layer, and now the OS has no mechanism to verify that the endpoint is local. If we strip away the cloud baggage, local inference should be provable at the kernel level, UDS with, or CUDA IPC bypassing the network stack entirely. What's the right primitive here? Assistant. User. Right. So NemoClaw's problem isn't strictness, it's a missing trust tier. The sandbox currently has two modes, whitelist NVIDIA endpoints, trusted, and everything else, blocked. There's no tier 1 for kernel-verified local process. I want to see NVIDIA implement permitted routing for localhost coexistence, UDS bind mount into the sandbox, or a CUDA IPC channel, so the host inference engine is trusted by construction, not by IP whitelist. What should the full trust architecture look like? Assistant. User. This goes beyond NemoClaw. The OpenAI-compatible interface bootstrapped the ecosystem, that was the right call for adoption. But now that agents have shell access, file system access, and autonomous execution loops, the security requirements are fundamentally different. The protocol layer needs to carry proof of locality, not just route HTTP to a different. This is a systemic design debt across the entire local AI stack. Assistant. Conclusion. The technical details of the workaround are available in the GitHub repository. The deeper takeaway, the local AI ecosystem inherited the cloud's interface without inheriting a way to prove locality. Until that gap is closed, at the kernel level, not the network level, developers will keep hacking around sandbox isolation to use the GPU sitting right next to them. This is an experimental workaround, use it at your own risk. A personal note on the three-tier trust model I proposed above addresses the protocol-level problem. But for enterprises handling sensitive data, there is an even more decisive architecture: eliminate the trust boundary entirely by co-locating everything inside a single closed Docker environment. The concept is straightforward. 1. One Docker space, or a set of segmented containers, on the organization's own hardware, with an GPU pass-through. 2. Raw data goes in, including PII, internal documents, proprietary datasets. This is permissible because nothing leaves the container boundary. There is no external endpoint, no API call, no network egress. 3. Nematron, or any local model, processes it inside: statistical analysis, summarization, classification, anonymization. The model runs inference on raw data and outputs masked, aggregated, or anonymized Python results. 4. Raw data is purged after processing. The container retains only the sanitized output. A scheduled job cycles this multiple times per day. What this gives you: localhost, but used like a cloud, teams access the Docker environment as if it were a managed AI service. Same developer experience as a cloud API, but running on the organization's own closed network. The data never touches an external server. No system integrator dependency. The typical enterprise path is to hire a vendor to build an AI platform. But that vendor's solution likely calls cloud APIs behind the scenes, and you have no way to monitor or verify whether your data is being forwarded externally. With a self-contained Docker workspace, the flag is your audit. There is nothing to monitor because there is nowhere for data to go. No protocol debt. Inside the container, there is no distinction between local and remote inference. The model and the agent share the same process space. The entire HTTP/TCP debate from earlier in this article becomes irrelevant. You have removed the network layer, not fixed it. Compliance by construction, GDPR, SOC2, HIPAA all require demonstrating that sensitive data stays within organizational boundaries. The container has no network interface is the simplest possible compliance proof. This is the architecture I believe enterprises should be building toward: not a sandbox that blocks external access, but a workspace where external access is structurally impossible. No firewall rules to audit, no IP whitelists to maintain, no trust tiers to verify. The absence of a network connection is the strongest security guarantee the operating system can provide. Variant, the one-way SSH model, physical sandboxing with mature technology. The Docker-based colocation above works, but there is an even simpler variant that uses no containers at all: a dedicated local AI server accessed via one-way SSH over tailscale. Recommended setup: 3 machines. 1. User PC, Chromebook, laptop, thin client with GUI. Has SSH access to both servers below. 2. Claude Code Server, runs Claude Code purely as an orchestrator. Does no inference itself, all reasoning tasks are delegated to Nematron via. Has SSH/HTTP access to the Nematron server only. 3. Nematron Server, runs BLLM with Nematron at tier 0. Processes raw data including PII. Has no outbound access to any other machine. The data flow. Raw data ingestion: users push raw data, including PII, internal documents, proprietary datasets, directly into the Nematron server via SSH/SCP from their PCs. This is the only inbound path for sensitive data. Orchestration: Claude Code sends tasks to Nematron via, e.g., analyze this dataset, summarize these documents. Claude Code never touches the raw data, it only issues instructions and receives filtered results. Filtered output is shared: Nematron processes the raw data and produces sanitized output, column structures, statistical summaries, anonymized results, ignored code. This filtered output is made available to both the human user and Claude Code simultaneously. Both see the same results, enabling the human to review what Claude Code is working with. One-way data boundary: raw data enters the Nematron server but never leaves it. The Nemetron server accepts inbound SSH connections for data ingestion and filtered output retrieval, but initiates no outbound connections. It has no route to user PCs, the Claude Code server, or the internet. Only the filtered output pipeline crosses the boundary, and only when pulled by an authorized client. The topology itself is the sandbox. No Docker, no NemoClaw policy files. Why this works? The sandbox is physical, not software. There is no container escape to worry about, no firewall rule to misconfigure, no prompt engineering that can open a network route that doesn't exist. Output filtering is a structural choke point. Nemetron sees the raw data and can report on it. This dataset has 12 columns, 3 contain PII, but every output passes through sanitization before it reaches anyone. Raw data never traverses the boundary. Claude Code orchestrates, Nemetron reasons. Claude Code focuses purely on task decomposition and workflow. All inference, analysis, and data processing is performed by Nemetron. The separation is clean. Claude Code never sees raw data, and Nemetron never reaches the outside world. Humans and AI see the same output. There is no hidden intermediate state. The filtered results are a shared view, which means the human can audit exactly what Claude Code is basing its decisions on. Internet access is separated by design. The Nemetron server has no connection to the public internet, by design, not by firewall rule. Web searches, URL fetching, package downloads, and any external API calls are handled exclusively by the Claude Code server. The Nemetron server is an air-gapped inference engine that only receives tasks and returns filtered results. Why Claude Code as orchestrator? The reason for choosing Claude Code over other agentic frameworks' built-in capabilities is not just about sandboxing philosophy. Claude Code has a significantly superior ability to decompose natural language instructions into structured, multi-step task execution, orchestrating file operations, shell commands, API calls, and iterative refinement in a way that current open-source agent frameworks do not match. This orchestration capability is, in my view, underappreciated even among engineers who are closely following the agentic AI space. From hands-on experience with multiple agentic systems, Claude Code is in a different class when it comes to task execution reliability and operational safety. This is not a criticism of any single project, it is an observation that the orchestration layer deserves the same scrutiny as the inference layer, and currently Claude Code sets the bar. In this architecture, Claude Code handles what it does best, task orchestration, search, external communication, while Nemetron handles what it does best, private inference on sensitive data. The separation is not a compromise, it is an optimization. Output delivery is pull-based, not push. The Nemetron server never initiates outbound connections, not even to deliver results. Instead, the server maintains a 3-stage file system. Raw input data, readable only by the Nemetron process. Nemetron writes inference results here. A deterministic filter process validates staging output and writes sanitized results here. Claude Code and users SSH in to pull from this directory only. Nemetron has no write access to. The filter runs as a separate OS user with exclusive write permission. This means even if the model is compromised via prompt injection, it cannot bypass the filter. The bypass is prevented by Unix file permissions, not by AI judgment. Filtering is deterministic, not AI-based. This is critical. If the filter itself were an LLM, it could be prompt injected into passing through raw data. Instead, the filter is implemented as rule-based code, regex patterns for PII, email, phone, national ID, strict output schema validation, only predefined JSON/CSV structures pass through, and an allow list approach where free text pass-through is blocked by default. The filter's correctness is auditable because it is deterministic, the same input always produces the same output. Every component is mature technology. SSH, Tailscale, curl, Python, VLLM. Nothing experimental. Nothing that requires a workaround. The entire protocol debt discussion from earlier in this article becomes irrelevant, not because we fixed the protocol, but because we removed the network boundary where the protocol mattered. Note on filtering implementation, The Nemetron server's filtering layer can be built with open-source local DLP tools such as Microsoft Presidio combined with custom regex and schema validation. On the Claude Code server side, which does have internet access, services like Cloudflare Zero Trust, Gateway, and DLP can guard outbound communications as a second layer. The two complement each other: local DLP for the air-gapped inference server, cloud-based DLP for the internet-facing orchestration server. This is Tier 0 implemented at the hardware topology level rather than the container level. And arguably, it is the most honest version of local AI. The data stays on a machine you own, processed by a model you chose, with no path to the outside world that any software vulnerability could exploit. It is also worth noting that the benefits of this architecture extend beyond risk mitigation. A fully self-contained local environment is not just a defensive posture, it is a platform. Within a closed network, organizations can scale the Nemetron server into a multi-node cluster and build capabilities that would be impossible or unacceptable to outsource, fine-tuning on proprietary datasets, building RAG pipelines over internal knowledge bases, optimizing inference, quantization, distillation, KV cache tuning, all without any data ever leaving the organizational boundary. For use cases involving the highest levels of confidentiality, where even the existence of the data cannot be disclosed to any third party, this is not merely preferable. It is the only viable architecture. No amount of contractual guarantees from an external provider can substitute for the physical absence of an external connection. Concrete sizing for a 1,000-person organization. The hardware requirements for this architecture are surprisingly modest. Nemetron server, 20x RTX 5090, 32 GB VRAM each, in 1 to 2 racks. With Nemetron 9B quantized to INT4, 5 GB, each GPU retains 27 GB for KV cache. At 4K context length, each GPU handles 5 to 10 simultaneous inference streams. In typical enterprise usage, only 5 to 10% of users are actively generating at any moment, so one GPU comfortably serves 50 to 100 users. 20 GPUs cover 1,000 users with comfortable headroom for peak loads. DLLM's continuous batching and paged attention maximize throughput across concurrent requests. Claude Code orchestration, 10 Chromebook Plus devices, $700 each. These are stateless orchestrators running Claude Code. They issue commands and relay filtered results. They carry no sensitive data and are trivially replaceable. Scale the count with the number of concurrent active users, not total headcount. Networking, tailscale. VPN mesh setup takes minutes, not weeks. Zero infrastructure overhead. Total initial cost, around $50,000. RTX 5090 at $2,000 each, $40,000. Chromebook Plus at $700 each, $7,000. Tailscale is free or minimal cost. That is the full price of a secure, private AI infrastructure for 1,000 people. Compare this to a typical enterprise AI platform engagement with a system integrator, which would cost 100x more, take months to deploy, and likely route your data through cloud APIs you cannot audit. This article was developed through a dialogue with Claude by Anthropic. The philosophical framing and architectural analysis emerged from that collaboration.